All right, so the last part of this section is about friction. So remember that friction is a force that opposes motion. Force that opposes motion. So it doesn't matter if it's standing still or moving, it opposes motion. And this comes from the surfaces. Surfaces, if you zoom in, are rugged, they're rough. Even if they're sanded, they're still rough. So what it is it's these two surfaces pushing against each other. That's what friction, that's where it comes from. It's down at the molecular level. And there's two types of friction that we talk about. The first is static friction. And the symbol for static friction is going to be a little f with an S. And then we have kinetic friction. And this would be F with little k. All right, so static friction. Static friction is, I don't know, I like to say it's like stickiness. So this is when things are not moving relative to the surface. To a surface. This last statement is important. This will help you make sense of stuff. So if I have a box on a cart and the cart is moving with velocity, then it's static friction. The box is not moving relative to the cart. So it's actually a static friction force that's holding it in place. Because the box has inertia and wants to go this way. So we actually have a static friction force this way. Now, if I'm pushing something against the floor and it's not moving, so if I have a rope and I'm pulling it with some tension, then static friction acts against it. It just doesn't want to move. Whichever way the box wants to go, friction acts against it. In this case, if I pushed it real fast, this would fly off because of inertia. Well, it doesn't, and that's because of the static friction acting in the opposite direction. But the idea is that it's not moving relative to a surface. Kinetic friction, on the other hand, is when an object is moving relative to a surface. To surface. So this would be, suppose I'm actually moving, I'm actually tugging a block with tension, so there's some velocity, then I'll have some kinetic friction acting backwards, resisting the motion. So if I remove this, if I take away the tension, it's going to stop because my net force then is backwards, and I would end up with acceleration in this direction. Okay, so how do we calculate it? Well, friction in general, the force of friction, that's how it looks on your equation sheet, is less than or equal to the coefficient of friction times the normal force. So we're going to come back. This is why we just did normal. And this is the coefficient of friction. Coefficient of friction. It's a measure of the, it's the stickiness between two surfaces. So if it was ice on ice, you would have a very low coefficient of friction. Concrete on concrete, very high. So high coefficient of friction. The coefficient of friction goes from 0 up to 1. Sometimes can be equal to. Of course, if it's equal to 0, then we have no frictional force. So it's actually between. And then 1 would be a maximum, although in reality we can get values greater than 1. Melting rubber on a road, that sort of thing. Let's see, what else? Okay, so how about some examples? Calculating friction. Get a new page open. All right, so suppose you have someone and they're trying to move a sofa, trying to move a couch. So they put it on those little, those little sliders that you can put underneath to help you push it. And the coefficient of kinetic friction is going to be 0.080. The coefficient, there's no units, by the way. No units. It's unitless. The mass of the sofa is 32 kilograms. And then she's pushing it with a constant velocity of 0.40 meters per second. And that's constant velocity. So you have some velocity going this way. What force is being applied? So how much force is being used to push it? All right, so let's just think about a free body diagram or a force diagram. So we know that we have some weight, and weight is equal to mg. And then because we have weight and we're on a surface, we're going to have the normal force coming up. And then we're applying a force in this direction. But because there's friction, we're going to have some friction coming backwards. And since it's moving, this is kinetic friction. All right. So the first thing we may want to do is just set it up. It's at constant velocity, so that means that the net force is equal to 0. So let's add up the forces. And all we care about the motion is this way. So this would be the force plus the friction force is equal to 0. So the force applied is going to be equal to the opposite of the kinetic frictional force. But now we need to change this. So the friction force, if you remember, force of friction is less than or equal to the coefficient of friction times the normal magnitude. Oh, by the way, this is for static. Static friction will go up to a max, and then it breaks free, and then it becomes kinetic. We did this in class, so that'd be kinetic friction. But there's a maximum. Once it hits kinetic, then it's equal to. So we know we're going to have the opposite of the coefficient of kinetic friction times the normal. So now we have to figure out the normal. Well, since it's a horizontal surface, then the normal cancels out or is equal to the weight in the opposite direction. So the force is going to be K times mg, but g is negative, so this all becomes positive. So we substitute in and get our values. And that's it. That's how we would deal with that. Should we do an angle? That was with kinetic. How about static friction? Let's say, I don't know. So we have a box sitting on an inclined plane, but it's not moving. We'll have a mass of something. What's the, I don't know, what's the coefficient of static friction? Okay, so we have a box of mass m on a plane, but it's not moving. So what we need to do is we need to, that's what I want, that's not a force. We need to draw a force diagram. So we're going to have the weight coming down, and then we'll have the normal coming up perpendicular to the plane. We're calling this x and y in this direction. X, y. All right, so we can see we're going to have to add some components. Oh, this is the static friction force. We'll go ahead and add in some components. So that would be my angle. This would be weight in the y direction and weight in the x direction. All right, so since the box isn't moving in the y direction, the net force in the y is equal to 0. So the normal plus the weight in the y direction is equal to 0. So the normal is equal to the negative of weight in the y. And then we can change that. It's next to the angle, so we can use our trig. So the normal is going to be negative w cosine theta. And weight, we calculate that with mg. So the normal is negative. I'm going to go to make it positive because mg, the g is negative times negative is positive. cosine theta. So that's my normal. Now we can go to the x direction. So the net force in the x direction is also equal to 0. But you might look at this and say, well, there is a net force. It's the static friction. But you got to remember there's a force down here. So we have the weight in the x direction. So we have the static friction force plus the weight in the x direction is equal to 0. And to calculate static friction, that's the coefficient of static friction times the normal plus W in the x direction is equal to 0. So we have, with some substitution, the normal, we get coefficient of static friction. Sorry, I got sloppy. mg cosine theta plus Wx. Wx would be the weight times sine theta, or mg sine theta, equals 0. And now we can move this over and then divide. So we get the coefficient of static friction is going to be negative mg sine theta divided by mg cosine theta. But again, g here is negative, so we'll make that negative. I mean positive. And actually all of this cancels. So we just get sine theta over cosine theta. And that would be our coefficient of static friction. All right, so that's how you analyze friction. Go ahead and go do some practice.